Hello everyone, myself and Uday Ranjan Goud, working as Assistant Professor in Department of Aeronautical Engineering, MLR Institute of Technology. So in the previous modules, we completed Unit 1 and Unit 2, and in Unit 2, we completed in the last session, that is unsymmetrical bending of the beams, direct stress distribution, and we have seen for various sections how to find out direct stress due to unsymmetrical bending, and followed by tension field beams, complete tension field beams, and incomplete tension field beams, and the post buckling behavior of plates. Now we are going to start Unit 3, and this is basically deals with the shear of open and closed section beams. So we are going to see we have seen already unsymmetrical bending of the beams in Unit 2. Okay, so now we are moving from bending to shear. Now here we are going to see how the shear forces will act on the beams, and how they are going to create impact in the analysis of calculation of stress distribution, maybe the shear stress distribution, and followed by the shear flow. So, and we are going to see the shear flow in open section beams and in closed section beams, and thereby we define a particular term called shear center, and we are going to see how to calculate the shear center for open and closed section beams as well. So, and then we are going to see the combined bending and open and closed section beams as well. So the first module, here we are going to see the shear loaded thin wall beams, and basically these are associated with stress, strain, and displacement relationships. So the learning outcomes in this module are, you are going to differentiate between bending and shear loads, and the students are able to analyze stress, strain, and displacement relationships. Basically, when it comes to bending and shear, and for example, you will consider a beam, and on which if you try to apply the bending moments on both of the ends, then it's going to create bending. That means the beam is going to bend about a particular point. So therefore, now for example, with this, let us assume that the beam bend in this manner. Okay, and you are going to find out the bending effect of this due to the application of bending moments. Now the shear loads. Now for example, if you consider a two-dimensional body, and these shear loads are usually they act tangential to the surface, and you may have like horizontal shear load Sx, and you may have vertical shear load, that is Sy. So these act tangential to the surface, and these shear forces in turn, they induce shear stresses in the beams. So therefore, along with the bending, it is essential for us to study the shearing effect in the beams as well. So in bending, we considered thick beams, and then we later on extended to the thin wall beams, and but in shear, the theory is limited only for the thin wall beams. So you are going to study the shearing effect in the thin wall beams only, and we know that we have neglected shear in the previous unit because we considered their bending, and we didn't consider the effect of shear. Now here we are going to consider the shear load, and along with the bending loads, the shear loads also may be present in the any beam cross section, so that the effect of the shear load should be considered in the analysis, either to calculate the stress distribution, or either to calculate the displacement associated with these shear forces. And so therefore, since we are extending our concepts from bending to shear, and it is very much essential for us to establish a relationship between the bending moments, shear forces, and the loads that we apply on any beam. So moving on here, and we'll consider one small element which is drawn over here. So small rectangular element we consider here, and we are going to represent all the possible forces on this element. So let's try to look out the forces on it one. So we are going to study about stress, strain, and displacement relationships of open and closed section, single section thin wall beams. And for that, we are considering an element, and whose dimensions are delta S cross delta Z cross T of the beam wall, and it is maintained in equilibrium by a system of direct and shear stresses as shown in figure. So let's look into this forces and how they are applied, where they are applied on this element delta S cross delta Z cross T. So there are two diagrams which you are able to see here, and first we will try to understand the first diagram, and then let's move on to the second diagram. Next we'll move on to the second diagram. So if you look at the first diagram, first let's try to see first direct stresses that are encountered on the element. First direct stresses. So for example, since like XY axis system, so we considering delta S in X direction and delta Z in Y direction, like that, and thickness T is there in Z direction. And so as we know very well that since we are dealing with the thin wall beams, and the thickness is kept minimum, very much less when you compare with the lateral dimensions, that is delta S and delta Z of the plate. So first the plate dimension, let's see. So this is a plate dimension, and the delta S is the dimension, horizontal dimension of the element what we consider, and delta Z is a vertical dimension what we considered, and then the thickness is T. Anyway, thickness is T, so it is uniform throughout, so thickness is T. And now we are going to represent the direct stresses on this one. So let us assume that if the direct stress perpendicular to this edge along X axis or S axis, so that is sigma S, and on the other edge opposite to it, so the stress will be delta S plus dou delta S by dou S into delta S, so that we are representing delta sigma S along with some increment. So sigma S plus dou sigma S by dou S into delta S. And if you look at the other edge, so sigma Z is the stress on this edge, and on the edge opposite to it, so there is an incremental direct stress, that is sigma Z plus dou sigma Z by dou Z into delta Z. Okay, so and now here we are writing, because as you move along this along S direction, so there will be increment in X direction. Similarly, as you move along Z direction, there will be increment in Z direction, so that you have to understand. So sigma Z plus dou sigma Z by dou Z into delta Z, that will be the stresses parallel to Z axis. Okay, right. Next, let's try to represent the other stresses as well. Okay, right. So let's try to represent now these four stresses we represented. So four stresses. One is sigma Z and its increment plus increment, and second one is sigma S and its increment. So total there are four stresses that we have represented on this element. Now let's try to represent the shear also. So shear force, that is shear stress, that is now here it is tau Sz. Okay, so if you assume shear stress tau Sz in this direction, and on the edge opposite to it, it will be in opposite direction, and that increment is given here, that is tau Sz plus dou tau Sz by dou S into delta S. And similarly, tau Zs is the shear stress along this edge, and therefore on the other edge the increment will be opposite to it, and then it is represented by tau Zs plus dou tau Zs by dou Z into delta Z. Okay, so again when it comes to the shear stresses, again we are going to represent four types of shear stresses. One is tau Z and plus its increment, and next one is tau Zs plus its increment. So totally there are four shear stresses we are representing. So four direct stresses and then four shear stresses that we are representing on the element delta S cross delta Z cross T. Okay, so this is what we understand from the bending shearing actions that simultaneously act on any beam element. Okay, now what we are doing in the second diagram, if you look at into this diagram, so what we are doing here, it is we are replacing because thickness also there here, so thickness also there, and bending is there, shear stresses are there. Now what we are doing here, the shear stresses, especially the shear stresses whatever they are there, 4 shear stresses, and these 4 shear stresses, and by considering thickness of the plate, and we are removing them and replacing by a new term called shear flow, and which will be represented by Q. So the shear flow is defined as shear force per intensity. So instead of keeping shear stress and thickness, again if you add thickness, it's going to give 2 more variables, and the analysis when you go through for finding the stress distribution is going to little complex. So if you want to, so we'll try to reduce the calculations in the analysis by introducing the term called shear flow, and which is defined as shear flow, that is Q, that is equals to, which is defined as tau into T, okay, or shear stress, that is defined as Q by T. So shear force per intensity. So again here it is what we have, the shear flow. So we are going to represent in terms of shear flow here in the second diagram. So let's look into this one. For example, tau Sz is a shear stress over here, and then we are going to replace it by Q. So Q is the shear flow, okay, and also tau Sz and tau Zs, 2 shear flows we are using here, but we know that from the complementary nature of shear stresses, we can write tau Sz equals to tau Zs equals to simply tau, okay, from the complementary nature of shear stresses, because these shear stresses are equal in magnitude but opposite in direction. So we can represent by T, and by considering tau multiplied by T, so that will give you shear flow. So you are adding shear stress, you are adding thickness of the wall, and these two things together you are putting in a form of shear flow, and that is being replaced in the second diagram. So that's why you got Q here, and once you get Q on the edge opposite to it, and you are representing with respect to the increment, that is Q plus dou Q by dou S into delta S. Similarly, on the third edge, again the shear flow you can consider as Q, and then on the other edge opposite to it, the increment will be Q plus dou Q by dou Z into delta Z. So we are going to consider the second diagram, okay, and to find out the relationship between stress, strain and displacements for open and closed section beams, and in fact we are limiting our discussion to the single cell section, and later on if you want you can extend it to the 2 cell or 3 cell sections, okay. So this is what, and now we are going to write the equations from this second diagram. So it's very important to us to draw this. Once you draw this diagram properly, and you can write the equations from the diagram itself, okay. So you can see here thickness is also placed over here. Let's look into this, what we going to write now. So the direct stress sigma Z is produced by bending moments or the bending action of the shear loads, while the shear stresses are due to the shear and torsion of a closed section beam or shear of an open section beam. So we express shear flow as the shear force per unit length or shear force per intensity rather than in terms of shear stress, and in such a way that the Q is written as Q equals to tau into T, and it is assumed that the shear flow Q is constant across the walls, across the beam walls. We assume that shear flow is constant across the walls. So shear flow is constant across the beam walls means, again the product of tau and T is also constant, so that you can write for walls, you can write for example tau 1 T1 equals to tau 2 T2 equals to, and so on, that you can keep it as constant, okay. So now when you are going to the equilibrium, so for the equilibrium of the element, and we are considering the in Z direction, and we are neglecting the body forces, and we are trying to write the equation. So what is that equation? And you are considering in Z direction. Now look at the forces, what are that there in the Z direction. So just go back and see the forces. So in Z direction, so you have sigma Z increment in Z direction, you got sigma Z in Z direction, and also you can see this Q is acting in along parallel to Z direction, and this Q increment is also you're having parallel to Z direction. So these are the four possible forces that we are going to add them in the equilibrium equation in Z direction. So for analysis, you can consider these incremental direct stresses as positive, and you can consider as negative, so that this will also be, you can get negative and this you will get positive, vice versa. It is up to you. Okay, so either you can consider downward force as positive, or you can consider upward force as positive, but you have to take vice versa, right? So now the sigma z plus dou sigma z by dou z is the stress, and it should be multiplied with the area on which it is acting. So the area on which it is acting is nothing but ds into t. Okay, and then it becomes the force, because these are the stresses, so it should be multiplied with the area to make them to convert into the force for considering as in the equilibrium. So with that, what we have here, sigma z plus dou sigma z by dou z into TDS is the area, and on the other edge sigma z into TDS, and similarly Q plus dou Q by dou S into delta S, and into delta Z is shear flow. Now how to write shear flow? Because we consider shear flow as shear force per unit length, right? Shear flow Q. So therefore the Q should be multiplied with the length to get the shear force. Okay, so you have to look the shear flow is acting on which edge. So if you go back to the diagram, the shear flow dou Q plus dou Q by dou S into delta is acting on this edge, where this edge length is nothing but delta Z. Similarly, this Q is also acting on this edge, where its length is nothing but delta Z. So you have to multiply the shear flow with respect to the length on which it is acting. Okay, so that is nothing but delta Z for this case. So therefore Q plus dou Q by dou S into delta S into delta Z minus Q into delta Z equal to 0. Okay, and in this you can see clearly that sigma Z into TDS gets cancelled with this, and Q into delta Z gets cancelled with this, and you left with only two terms here. One is this term and the other one is this term, and that is dou sigma Z by dou Z into delta Z into TDS plus dou Q by dou S into delta S into delta Z, that is equal to 0. So now we are going to reduce the form of the equation. Okay, and when you try to reduce the form of the equation, and what you can write here, it is delta Z and delta S, delta Z and delta S are common in these two equations, and you can take out, and you can write first this equation, that is dou Q by dou S plus T into dou sigma Z by dou Z equal to 0. Okay, so this is the equation what we are going to derive. This is very, very important equation, and one must remember this equation, because in the next session we are going to derive the shear flow in open section beams formula. So the shear flow in open section beams formula starts with this equation. Again, you should not consider where we get this equation from. Okay, so we got the equation by considering the equilibrium in Z direction, and we are going to use this equation to find out the shear flow in open section beams. So it's very, very important equation. So dou Q by dou S plus dou sigma Z by dou Z equal to 0. So that's what, it's very, very important equation to remember. Okay, similarly, if you try to consider the equilibrium in S direction, you are going to get dou Q by dou Z plus T into dou sigma S by dou S equal to 0. So the direct stresses sigma Z and sigma S produce direct strains, that is epsilon Z and epsilon S, while the shear stresses tau induces shear strains, that is gamma ZS and gamma SZ, or you can make it as gamma if you consider them equal in magnitude and opposite in direction. And now we'll express these strains in terms of the three components of the displacements of a point in a section wall. So if you try to see here, there are two strains, that is epsilon Z and epsilon S, which are the direct strains, and you have got two shear strains as well, that is gamma ZS and gamma SZ are the two shear strains. And let's try to represent all these strains into the displacement, and so as three components of a displacement. So whatever, if you try to take one, consider one point, so this point, if you want to define strains, it's associated with three types of strains. Okay, So three types of strains. So the displacements that you are going to write in three components of, okay, so that we will see how we are going to write the displacement in three components. So for understanding that displacement, so we consider this diagram and let us assume a point on any arbitrary section and about which you are going to represent the displacement components. So you can see here first that is Vt is nothing but the tangential displacement. When you draw a tangent to the point where you are considering on any lamina or any arbitrary section, so Vt represents the tangential displacements and Vn represents the normal displacement, and then you got one more thing, that is W, which is nothing but the axial displacement. So if you want to find out strain at any point, and usually it is associated with three types of displacements, that is tangential displacement Vt, normal displacement Vn, and axial displacement W. Okay, so these axial, tangential and normal components of displacement are used to establish the relationship between stress, strain and displacements. Okay, so Vt is the tangential displacement in xy plane taken as positive and in the direction of increasing S, and Vn is a normal displacement and W is the axial displacement. Okay, and now from this analysis you can write two direct strains, that is epsilon z, that is straight away you can write epsilon z as dou W by dou Z. So epsilon z, if you are writing in z direction, so in z direction the displacement component is nothing but W, so you are writing with respect to z, so this is just like strain in x direction, that is dou U by dou X. Okay, we'll write epsilon x equals to dou U by dou X. Similarly epsilon z equals to dou W by dou Z, which is the direct strain. And once you got epsilon z, and next if you are writing epsilon s, so epsilon s is nothing but this one, epsilon s, which is nothing but the tangential. Okay, so you are writing tangential direction and then followed by the normal direction in x axis as well as y axis. So therefore what you are writing here, it is possible to derive a simple expression for the direct strain epsilon s in terms of Vt, Vn and S, and the curvature 1 by r in the xy plane of the beam wall. So now what you are going to write epsilon s direct strain is nothing but what? First dou Vt by dou S, which is nothing but similar to this one. Okay, so first you are writing with respect to this dou Vt by dou S, that is epsilon s, that is equals to dou V2 by dou S, plus next we have to write along with the curvature, that is normal component. So and if you try to write in the other direction, it is associated with two components. One component is tangential component and other component is normal component, and you are writing with respect to the curvature. So the other component will be normal displacement divided by r, which is the radius of curvature. So that is epsilon s. So epsilon z and epsilon s are the direct strains that we are going to get here. And now the shear strain gamma is found in terms of displacements W and Vt by considering the shear distortion of the element delta S cross delta Z of the beam wall. So what is the shear distortion? For example, a normal component, for example, if you have a normal component like this, so because of the shear forces or shear stresses that exist on the beam, so you may get a beam like this, you may get distortion like this. Okay, so because of the application, what you are going to apply tau Sz, and on the other tau Sz, and here you are going to apply tau Zs, and here you are going to apply tau Zs. So because of this, what happened? So this distortion of the element will occur, and by considering all these effects, we are going to establish relationship for gamma, that is the shear strain. Now if you look at this diagram clearly, what you can understand, this is a normal rectangular element we considered, which is nothing but delta S, and this one you can consider delta S edge, and this one is delta Z edge. And now you can see clearly by the application of the shear stresses on this one, So the shape is going to distort. So this is the distortion what you are able to see here in the diagram. This is the distortion. From that means it will move away from its original cross section. Okay, while it is distorting, so it creates a slope, and you can assume that phi 1 is the slope along s direction, and phi 2 is the slope in the y direction. That is, it creates a slope like this. Okay, and followed by the lengths what it reduced, you can consider in this direction. That is, dou w is the displacement what we have here, and dou vt is the displacement over here. Okay, so the shear strain now is a combination of phi 1 and phi 2, because that is what the distortion we are getting. So therefore, along s direction there is a distortion, that is slope is phi 1, and along z direction and there is a slope distortion, that is phi 2. So the shear stress is the combination of both. Shear strain is the combination of both, and from the simple geometry, and you can find out what is that phi 1. You can apply tan phi 1, and then for small angles of approximation you can make it to phi 1, and then you are going to get dou w by dou s. And the second one also you can apply tan phi 2 for the second diagram, and you are going to get dou vt by dou z. By adding together, you are going to get shear strain, that is gamma equals to dou w by dou s plus dou vt by dou z. So if you go back and see the shear strain in z direction is dou w by dou z, and shear strain in s direction is that is epsilon s equals to dou vt by dou s plus Vn by r, and now the shear strain is nothing but gamma equals to dou w by dou s plus dou vt by dou z. So these are the shear strain, direct strain and shear strain associated at any point. And next, what we are doing here, the tangential displacement. Now if you consider any arbitrary lambda, and if you try to extend for a general category, like it may be for open or closed section beam, the tangential displacement Vt of any point n in the wall and is given below. Now what we are try to establish the relationship for tangential displacement Vt. Okay, for this we are going to consider one arbitrary cross section like which is shown here, and you can consider xy axis system, and Vt is the tangential displacement, and at point n. So at this point n you are going to draw one tangent, and you are giving it as Vt. Okay, and now to get the relationship for this Vt, tangential displacement, for any arbitrary section in either in open or closed section beam, we are considering one point r here. Okay, and which has coordinates xr and yr. Okay, and now the distance from the point r to this tangent is nothing but taken as pr, and similarly the distance from the origin to this tangent is taken as p, the distance, and then you have the two components of displacement, that is u in the x direction and v in the y direction. And what we are doing here is, and so first we are drawing one dotted line onto the x axis. Okay, and where it is connecting the x axis, and we are drawing one perpendicular which connects that is O to the tangent line and this line, and we are connecting this one, and then this is the angle what we are considering it as psi, angle psi. Okay, so PR is the distance of a point R to the tangent, P is the distance from origin to the tangent, and then psi is the angle that is created over here. By using these all notations, and we are going to find out established relationship between what is Vt. So for getting this relationship, so this is what relationship we got, and let's see what we are going to do. So here how many are there, and one u is u and v are the displacement in x and y direction, and theta is the rotation that we have to understand. So totally there are three types of displacement that are associated, that is u, v and theta, to find out the effect of Vt tangential displacement. Okay, so these displacement in a loading case such as pure torsion are equivalent to a pure rotation about some point r, xr, yr in the cross section where r is the center of twist. So from the diagram, what we are writing here, first we are writing for Vt. So the tangential displacement is associated with from point R to here, the displacement is R, and then the rotation is nothing but theta. So we are writing first instant, that is Vt is equals to PR into theta, PR into theta, and then we are going to write what is PR from this expression. Okay, so PR from the diagram. So you can see here what is PR, and so PR, for example, so from here to here it is PR, that is there in the diagram. And if you try to write this one, so up to here, from here up to here, from here to here it is P, right? So first we are writing PR equals to P, first this one, and next we are going to add what is this distance from the diagram. Okay, so that distance from the diagram, how you are going to get, and you are going to get through this one. Okay, so through this diagram. And what is this diagram? So for example, so you want to get this distance from here to here. Okay, and this is the angle, and if you try to apply, so usually if you consider this one, so this is considered as XR and this is considered as YR, and the angle what we taken is this one side. Okay, and again you have this one, right? So this is how we take this one. So now from this diagram, and what we are considering here it is, and you can consider this as Y as positive and X as negative, and usually this component of displacement is taken as, you know, sin psi. If you apply opposite sign, that is XR by hypotenuse. So this hypotenuse, let's consider H. So from this H you can write it as, it is nothing but XR sin psi, and which is nothing but negative. And if you try to apply cos here, so cos psi, that is equals to YR divided by H, and therefore H equals to, you can write it as YR cos psi, in which you can consider this as positive. So we are going to use these two. One is XR, that is height, both height you are considering here. So one height is this one minus XR sin psi, and the other height is nothing but YR cos psi. So which you are going to add these two as the lengths from here. So first, as it is, we are adding here. So P minus XR sin psi plus YR cos psi. So this is the PR. Now we are going to take this and substitute in place of PR. So you are going to get the tangential displacement Vt as P into theta minus XR into theta into sin psi plus YR into theta into cos psi. And then now we are integrating, differentiating this equation with respect to Z, so that you are going to get dou Vt by dou Z, that is equals to P into d theta by dz minus XR into sin psi into d theta by dz plus YR into cos psi into d theta by dz. So this is nothing but dou Vt by dou Z. And also from equation 1, and also what we are doing here, that is now we are putting in terms of this one, and dou u by dou Z. First, dou u by dou Z is equals to minus XR sin psi, that we have seen earlier, and dou v by dou Z, that is the second displacement, you got plus YR cos psi. So we are removing this, that is we consider like H, right? H. So now this dou u by dou Z, so minus XR sin psi plus YR cos psi, we are going to represent in terms of the displacement, that is u and v. Okay, so when you represent in terms of u and v, and this will be replaced and written as dou u by dou Z, and YR cos psi is removed and replaced by dou v by dou Z. So this is another equation what we got. So these are the equations, displacement relationships, which we have to understand for the displacement associated at any point in the beam cross section, which may be the arbitrary section, open or closed section. Okay, so these are important relationships what we got here. This is one relationship, and this is another relationship, and also probably this is another relationship which we have to remember. Okay, also try to remember that in the earlier we have seen the expression for the equation, that is dou q by dou s plus t into dou sigma z by dou z equal to 0, which relates the shear flow and the direct stress distribution. Okay, so that's it for today's session. and we'll catch up in the next session by considering the shear of beams, shear flow in open section beams derivation. So thank you everyone for watching.